So let's take a look at 5.1, which is on exponential functions. So let's just start by looking at the difference between x squared and 2 to the x. In each case, you have a base and you have an exponent. In the one that I just circled, which one is the base? Yeah? X. And which one is the exponent? Yeah.
2.
Yep, 2. Okay, so let me write that down. So the exponent is always the number that's up higher. The base is always what's below. Now the big difference between these is one of them is a polynomial, specifically a quadratic. The other one is an exponential expression. One on the left is a polynomial that's a quadratic. The one on the right, that is an exponential. What makes something an exponential is when you put a variable in the exponent. If you put the variable in the base, that's a polynomial. Okay, and that's what we studied a lot in chapter 3. So if the variable is in the base and the exponent is a number that is a non-negative integer, so remember integer means it can't have any fraction or decimal, that's a polynomial. Okay, so things like x cubed or x squared plus 2x. Anything like that. Those are all polynomial expressions. They're not equations. Those are just expressions. First one is a cubic, second one's a quadratic, and the third one is a quartic polynomial expression. Now, when you switch it, so that two things have to happen. The variable has to be in the exponent, and the base has to be a positive number that's not 1. That's an exponential function. So if I write f of x equals 3 to the x, that is an exponential function. You could say equation. Okay. G of x equals 1/2 to the x. That's also an exponential function. There's a big difference between the two of them. We're going to talk about one's growth, one's decay. And the growth or decay is controlled by the number that's in the base. How come 1 to the x wouldn't be an exponential function? I can do any positive real number bigger than 1 or smaller than 1. Not 1. Yeah?
So it's always equal to 1.
Yeah, if you graph y equals 1 to the x, it's basically just like graphing y equals 1. It's just a horizontal line. So the base has to be positive, and it can be bigger than 1 or smaller than 1, but not 1. So any question on what makes something an exponential? And if the base is negative, then really weird things start to happen. You can't really even graph something with the base being negative. Because if you think about like negative 2 to the x. Okay, start making a table of values for that. If you raise something to the 0 power, what do you get? 1. Okay. Now, what if you plug in 1? What's negative 2 to the first power?
Negative 2.
Negative 2. Now, what's negative 2 to the second power?
4.
4. How about to the third power?
Negative 8.
Negative 8. So the y values are bouncing all over. They're oscillating between positive and negative. And then if you did something like this, if you raise something to the 1/2 power, what does that mean to do to it? It means to square root it. And what's the square root of negative 2?
It's imaginary.
It's imaginary. So now y is I square roots of 2. So when the base is negative, all kinds of weird things happen. So that's why it has to be a positive number, not 1. Yep.
I'm sorry. With the way that goes like up and so up and down for the y value, is that similar at all to like sine, cosine? Like I've seen like graphs where it's like when you plug sine in or cosine, like the thing with the triangles, it makes it like a whole like wave thing.
Yeah, so sine and cosine does oscillate up and down, but there's a limit to it. This would just, if you went by integers, this number would just keep like doubling.
It'd start making like a sideways triangle, basically.
Yeah, you wouldn't see it though, because then in between all these values, then you have weird things happening, like imaginary numbers.
Yeah.
So all of a sudden, between 0 and 1, you start getting imaginaries. But if you did to the 1/3 power, that would be okay, because to the 1/3 power is a cube root,
Which is
and you can do the cube root of -2 and actually get an answer. So some fractions have imaginaries, some don't. You wouldn't see any picture if you type this in on the calculator. Wouldn't show it.
So what's happening when you put 1/2?
1/2, that's the square root of -2. Yeah. And then 1/3 would be the cube root, which you can do. 1/4, you couldn't. So yeah, it starts to get really messy with negative bases. Right, so this is basically the same thing I just said, but written a little bit more formally. The base on an exponential can be any positive real number, except 1. And the domain of exponential functions is all real numbers. You can plug anything in for the exponent. You can plug in positive numbers, negative numbers. You can plug fractions in, decimals. There is no restriction on what number you can let be the exponent in an exponential function. The base, yes, there are restrictions on the base. So here's
the A thing mean?
what's A?
No, that little thing on the domain.
Oh, the symbol after the A? That means element of. Or A is in the set of positive real numbers. That's what that symbol means. It means A is in the set of positive real numbers. Except for 1. So these are all examples of exponential functions. They all have bases that are positive and not 1. And they all have exponent variables in the exponent. These are all examples of things that are not exponential functions. What's this first one?
X cubed.
And what kind of thing is it?
trinomial.
Well, it's a monomial because it's a single term, but it's a that's a cubic polynomial. Cubic polynomials are not exponential. Specifically, it's a cubic polynomial with 1 term. This is a quartic polynomial. You could really think of it like this if you wanted. It's 1/2 x to the 4th. And the last one, that's kind of a combination of a rational and radical function, but it's definitely not exponential. All right, let's look at the difference between these two. 2 to the x and 3 to the x. So 2 raised to the x and 3 raised to the x. What happens as you start using negative exponents? Like if I did 3 to the -1, what does that mean? Yep.
That would be 1 to the 3rd, or 1 over 3.
1 over 3. How about 3 to the -4? Yeah. 1 over 3 to the 4th. Right. So what's happening as the exponent becomes more and more negative, what's happening to the value? Yeah.
It's getting closer and closer to 0.
Right. It's getting closer and closer to 0. And then all of a sudden, When you get past 1 for the exponent, that's when it's going to really start growing. 3 to the first is 3. 3 to the second is 9. By the time you get to like 3 to the 10th, it's off the screen. So it's going to look like it's flat or very close to 0 for a long time. And then after 1, it starts to curve up. So that's 2 to the x. And that's 3 to the x. What is it? What's it look like the difference is?
It's more nearer. Like the bigger the base, the more near it would be. Or
What do
like
you mean
more
by
steep.
Yeah, it gets steeper. It goes up quicker. Once you get past the y-axis, that's when it starts to curve up very fast. So 3 to the x would curve up faster than 2 to the x. Okay, and they do kind of switch places here, like we've seen with roots. When you are to the left of the y-axis, 2 to the x is a. When you get to the left, 2 to the x is. I forgot which one was which. 2 to the x is above the red one, and when you get after the y-axis, 2 to the x is below. So they switch places right at the y-axis. And if you put in 4 to the x, you'd see the same behavior. It would curve up even a little faster than the red one. So it would be like inside of it on the left. Now, does it ever reach 0 as you keep heading to the left?
No.
No. So exponential functions have horizontal asymptotes. Okay, so let's take a look at something. We already kind of mentioned that. When you raise something to the -1 power, it flips it. It puts whatever you were raising to the -1 power, it just puts it in the bottom of a fraction. So what I want to think about is what happens when we raise something to a negative power. But negative powers are confusing to think about. So to make it simpler, we're going to convert this negative power into a positive power. And what that's going to do is it's going to change the base, but make the exponent positive. Right, so let me show you how we can do it. What number is in front of that -x, even though it's not really? Right, it's like having, let me do it like this. It's like having a to the -1x. Now, if you put a -1 in front, what are you doing with the -1 and the x? You are multiplying. When would you end up multiplying two things together in an exponent? There's a rule for that. If you had
It would be
for a certain situation, you would multiply the exponents together. Yep. Right. If you had a power raised to another power, you would multiply them together, and you'd get a to the -1 times x. Now, we just said, what's a to the -1?
it would be 1 over
1 over a.
1 over a.
All that is.
So the point is this is exactly the same as that. So if you want to raise something and it has a negative exponent, and you don't want to think of it as a negative, because it's going to be confusing for some things that we do, just take the base and flip it, and then it can become positive. So if you had 4 to the -x, what would that be the same as without a negative exponent?
That'd be the same as putting 1 over 4 to the x.
Yep.
Or like 4 to the -1 power to the x, which is something.
Yeah, so what we'll do is if you have something with a negative exponent,
Make it a fraction.
yep, take the base and flip it, and that becomes your new expression. So any question on why that's true? The real reason for that is going to be because of exponential growth and decay. We want to make it easy to figure out if something is growth or decay. And the easy way to do it is to look at the base and determine if it's bigger than a number or smaller than a number. But it has to be a positive letter right there. You can't have a negative letter to make that trick I'm going to show you work. Okay, so we did all that. All right, let's look at this one. So find a complete graph of 2 to the x and 2 to the negative x. What's 2 to the negative x? What's another way to write it? Yeah.
1 over 2 to the power of x.
Yep. And the big difference between these is f of x has a base bigger than 1. G of x has a base smaller than 1. When you look at it like this, you may say that base isn't smaller than 1. Well, technically it is because it's, when you write it properly, it's 1/2 to the x. Okay. All right, let's graph each one and see what happens. So we've got 2 to the x. And just so I don't have to do fractions, I'm just going to do 0.5 to the x. And do zoom 6. Okay, there's 2 to the x. And then in red, you're going to see 0.5 to the x. How do those graphs compare to each other?
Flips over the y-axis.
Yeah, they're horizontal reflections. When you have a base bigger than 1, as you go to the right, curves up. If you have a base smaller than 1, as you go to the right, it goes down. Think about what happens if you keep raising 1/2 to a bigger and bigger number. Like half of a half of a half of a half of a half. It keeps getting smaller.
It's like the opposite of 2 to the power of x.
Yeah, they're opposites. They're both considered exponential functions. One of them is exponential growth. The other one is exponential decay.
Oh wait, it's right here.
Okay, so now let's look at the domain and the range of each of them. And I'll put the graph over here. Okay, so 2 to the x, that's the blue one. And that's the red one. What's the domain of f of x? Yep. Yeah, the graph is going to go left and right forever. It starts to go up quite a bit, but it does still go to the right as it goes up. So the domain for the blue one is all real numbers. How about the range for the blue one? Yep.
The range is going to go from 0 to infinity, but it's never going to touch 0.
Right. It's going to go from 0 to infinity, and it never reaches either 0 or infinity. How does that compare to the domain and range for the red one, g of x?
Same range.
It's-
Or same domain.
Same everything, yeah.
Oh yeah.
It's the same domain, and it's the same range. Now, we did that for a specific case where the base was a 2, but it wouldn't have mattered if I made the base a 3, 4, 10, 28. Wouldn't have mattered. It would have changed the steepness of the curve, but it would have had no effect on the domain or the range. In fact, which one of these can you never change, no matter what kind of transformation you do? Yeah.
Domain.
Yeah, you can't change the domain. Like, if you shift it right 2 units, it still goes negative infinity to infinity. Right, and we'll talk about the transformations. Like I'll show you the A, the B, the C, and the D, just like we did yesterday. All right, so now let's see if we can kind of generalize what we just did. If you want to look back, you can look at what's on the left. But the idea now is A could be any number. 2, 3, 12. If you want to make it concrete, pretend it's a 2. And then look back at what we did. When you have a graph that's exponentially growing, okay, like a to the x, as you head further and further to the right, what happens to the y value? What happens to the y value? In a graph like 2 to the x, or 3 to the x, or 10 to the x, as you head right, y heads to infinity. Yep. Now, how about in a graph like 2 to the x, as you head to the left, what happens to the y value?
Just 0.
It approaches 0. Again, it doesn't matter if it's 2 to the x, 500 to the x, it's going to follow those patterns. Now, look at something like g of x. That's more of a decay graph. As you head to the right on a graph that's decaying, what happens to the y value, Sophia? It gets closer to 0. And as you head to the left, it gets closer to infinity. So, all that happens is with growth and decay is which way you're heading. It always is 0 or infinity, but it just changes which one is 0 and which one is infinity.
So it swaps the y-axis.
Yeah, because it's a reflection over the y-axis. Yep. Okay, so the key difference, we've already kind of pointed this out a few times, but the key difference, whether it's going to be growth or decay, is look at the base. Is it greater than 1, or is it between 0 and 1? Will it ever be less than 0?
It will not be less than 0.
It will not be less than 0. It can't be. We talked about it. If it's less than 0, you start getting really weird answers.
It can't cross the x-axis.
No, exponential functions can cross the x-axis if you shift them.
No, like for the. But for this rule, like.
It can't go across to 0. Anything that's in the negatives doesn't work because it would be jumping up and down.
Yeah, we get all kind of weird values. All right, so the key difference between growth and decay, base bigger than 1 or a base between 0 and 1. No, not worried about that. So let me write that down. I think I write it down in a couple slides anyway, but greater than 1, that's called exponential growth. Between 0 and 1, that is decay. So we can transform exponential functions exactly the same way we've been transforming every function we've studied all year. All right. So your base function looks something like that. You've got a base, and then you'd have an exponent. So we could have shifting and stretching inside the exponent. I don't want to use a for the base, though. I'm just going to leave it as a blank box, because I need a for something else. And then you could have shifting and stretching outside the exponent. I'm not going to write down what each of them mean because we just did it yesterday, but I'll go through it. What would A do? What kind of transformation? Yeah. Horizontal shift. Positive would shift it to the left, negative to the right. How about B? It's still inside the exponent, but it's multiplication instead of addition or subtraction. Yeah.
Is it a horizontal stretch?
That's a horizontal stretch or compression. If it is a bigger number, it's going to cause it to compress. A smaller number causes it to stretch. So if you put in like a 2 for B, the way I would say it is horizontal compression by a factor of 2. If you put in 1/4 for B, I would say horizontal stretch by 4. Questions on that? Okay. How about C? Yeah.
I'm pretty sure that's a vertical version of B, where of a stretch or compression.
Yep. that's a vertical stretch. And there, you don't do anything backwards. If C was 5, I would say vertical stretch by 5. If C was 1/2, you could say vertical stretch by 1/2. And how about D? That's adding or subtracting, but it's outside the exponent. Yep.
So vertical shift up or down.
Vertical shift up or down. Positive is up, negative is down. And what about if B or C was a negative?
So the reflection on the y-axis?
Depends which one. If B is negative, that's a horizontal reflection, which means over the y. If C is negative, that's a vertical reflection. That's over the x. So it's the same as what we've done before.
In what order, like, does the reflection go when you write this down?
You can do the reflection right before or after you say the stretch.
Okay.
It doesn't really matter. So if you wanted like something concrete, horizontal shift, horizontal stretch, horizontal reflection, vertical stretch, vertical reflection, vertical shift. There's all 6. All right, so I just want to describe the transformations for this one. The base is not important. Whatever the base is on the transformation, that's going to be the base you compare to. So you're never going to compare like something with 3 to the x to something with 4 to the x. No, they have to be the same base. Okay, so first thing, how many transformations are happening in g of x? Yeah.
2 things. One, I think it's 4, and second of all, for the model thing to show all the things, A does the horizontal shift, right?
Yes.
What do the boxes mean?
Boxes.
In the model problem, like the C times box.
Oh, that would just be what your base is. Whatever your base is. I used A for the base when we started writing these down, but I can't use A because I'm using it for something else.
Alright. But yeah, I think it's 4 because you like you don't need to include the base in transformation.
So what's the first one?
The vertical compression by 2.
Okay, we always have to start with the A, then the B, then the C,
Oh.
then the D.
So a horizontal shift left, right. I mean left 1. Left.
So horizontal shift, left 1.
Yes.
And we don't have anything in the B position, so we don't have to.
A, B, C, D.
Yeah, alphabetical order, A, B, C, D. Can someone tell me the second thing that's happening? Yeah?
Second thing that's happening is, well, nothing. It's just a 1.
Yeah, so we can ignore B. So we skip B and then we go right to C.
Next up, then, is going to be the I'm pretty sure it's the one that I'm forgetting the name. Forgetting vertical or horizontal stretch.
That's important. It is a stretch.
I'm pretty sure it's vertical.
It is vertical. Anything that's outside the function that you're considering. Like in this case, outside means outside the exponent. When we did radicals, it meant outside the root symbol. Okay, so anything outside the exponent is a vertical. And then it's a vertical stretch, yeah, by a factor of 2. Okay, and then the third thing that's going to happen, this is the last thing. Shift down 5. So hopefully at this point you're starting to get comfortable with the transformations because they are the same. And when we do trig functions, even though you don't know what this is yet, I would hope you would be able to tell me what's happening there. The sine function is being shifted right 3 and up 2. Okay, it works the same for every function that we study. Any question on the transformations? Yeah.
If we did have B, what does B affect?
That's the horizontal stretch.
Thank you.
Okay, so So when you first look at these two functions, they look different, but they're not. They're exactly the same thing. So we're going to show that they are the same thing. You can start with either one of them. I would start with f of x and see if you can turn it into g of x. If you can, then that would show that they are the same. Let's see what I could do with the exponent first, just to make it look a little bit more like g of x. Yep. Okay, we can factor something out, and what else could I do? Yep.
Did you like change the order?
Yeah, let's change the order. I'll do it in 2 steps. So let's change the order. Now at least it's x number, and we could factor out a -2 from it. If you factor out a -2 from the exponent, what are you left with? Yep.
X negative 1.5.
X minus 1.5. And now what operation are you doing, well, with these two exponents? Yeah.
You can ignore the x minus 1.5 for right now and just deal with the -2 and the 2.
Right, because what are we doing right there?
It's multiplication.
Yeah, it's multiplication. So the only time you would multiply those exponents together is if you had, what would you have had originally that would have caused you to multiply exponents together?
Power to a power.
You would have had a power to a power. So 2 to the -2 to the x minus 1.5.
Which would,
And yeah, what's 2 to the -2?
it would go into,
It'd be
it
the
would
fraction.
turn into 1/4.
Right. That would be 1 over 2 to the 2 to the x minus 1.5, which is 1 over 4.
And when it's,
Or you could, if you want to write it as 0.25, you could do that, but
yeah.
you've shown that they are the same thing. Okay, so really it was factoring out that negative, rewriting the order, factoring out the -2, and then thinking that must have been a power to a power that caused you to multiply them together. So any question on how we showed those are the same? Okay. Not too worried about that right now. We're going to talk more about the number e when we do logarithms. It's kind of like pi. It's a special number. But we're not going to get to it until next academic week, so I'm not going to talk about it right now. If we were going to get to it tomorrow, then it would make sense, because then it would be close to when we're going to cover it. We have a test. Okay, so what I want to look at here is getting towards what we call an exponential growth formula. So this is going to be about a population of a town increasing every year at a rate of r. The rate would be a percent, like 2%. Anytime you have something that goes up by a percentage every year or every month, that's exponential. Increasing by a percentage is exponential. So let's look at year 1. Well, actually, let's look at year 0. When we start this experiment, how many, or whatever we're doing, how many people are in the town at the very beginning? Yeah? Yeah, there are p people in the town at the beginning. Now, to figure out how many people you have at year 1, the new population for year 1 is equal to the population you had the previous year plus how much growth there was. Assuming nobody dies off or moves away from the town or something. So the population for the new year is what it was before plus how much did it grow. Okay, that's the growth rate. So for year 1, what was the population the year before?
P.
It was P. Plus, we need to figure out the growth. To keep it simple, let's say there were 10 people. If you had 10 people and it grew by 1%, what can you multiply 10 by to figure out a growth of 1%? I want to grow that number by 1%. So it's going to grow, so it has to be a number bigger than 1. Yep.
0.01.
That would give me 1% of that number.
And then you add.
I want to grow it by that. Yep.
1.01.
Right. 1.01. If you did 10 times 1.01, that basically gives you what the growth is. Yeah, I see what you were saying. So we can think about it that way too. How were you going to say it, Diego? You take 10.
I was going to get the result of the 0.01%.
Okay. All right. Yeah, you can do it that way too, and then add it. I'll do it that way. So you can take 0.01 times the population from the year before, and then add it to what you already had. So in this case, population from the year before times your growth rate as a decimal. Now, what's P? Or actually, do it this way. What could you factor out of that? Yeah. You could factor out a P. And if you factor out a P, you're left with P times 1 plus R. Now let's figure out our population in year 2. And then I think you'll see a pattern. What was the population in year 1? Well, P was the population in year 0.
PR was the population growth in year 1.
Okay, P times R was the growth. So what was the overall population at the end of year 1? Yep.
Would it be P parentheses 2 plus R?
Not for year 1.
Oh no, for year 2.
Just year 1.
Oh,
What was the population in year 1? Yep. P times 1 plus R. Now you have to add to that the growth. And the growth is always what your population was times R. So P times 1 plus R times R. What do both of those have in common?
1 plus R.
Okay, so they both have,
They have the P times 1 plus R.
yeah, they have a P times 1 plus R. So let's do P times 1 plus R. And if you factor that out of the first one, what are you left with? Just, nope, the 1 plus R is gone. You're factoring the whole thing out. What would you put here so when you distribute, you get that back? Yep. 1. And then what would you put here? So when you distribute it, you get that back. Yep. What is it? R. And how does that simplify? P times 1 plus R times 1 plus R. P times 1 plus R squared. I actually had all the work, I just did it again. What do you think the formula would be for year 3? Yep. P times 1 plus R cubed. What do you think the formula would be for year T?
P times 1 plus R to the power of T.
Yep. So that's the formula for exponential growth. It's the original amount times 1 plus your rate of increase But make sure if they give it to you as a decimal, you make it a percent. I'm sorry, make sure you make it a decimal. So like 12%, 0.12. 3%, 0.03. And t, that's the time. Usually measured in years. But, yeah. So p times 1 plus r to the t. Yeah.
Can I ask two like kind of related questions?
Mm-hmm.
Alright, so one, half-life of like different elements. Is this some like I know we're going to go into exponential decay, but the half-life of like some
We're going to talk about that.
Alright. Okay, number
I'll
one.
hold off on that.
Yeah, and then so number two, just for like interest for banking and stuff like that, financial stuff, like that's probably gonna be on some tests and stuff. Is this similar to that? Where it's like, oh,
yes.
how much? Okay.
Yep. Banks would use an exponential formula. Yep. Now, if that's the growth formula, you only have to change one thing to make it decay. Anyone have a guess? What would change to make that a decay formula? Yeah, Sophia? Yeah, you just make it minus r. I'm not going to label everything again. P is still an initial amount. R would be the decay rate. And T would be how many years it's been decaying. Now, if the decay rate happens to be 50%, that's called half-life. Okay? When something is exactly a 50% decay rate, we just change R to a 1/2. Or 0.5. So we have a town with a population of 50,000 people going up 2.5% every year. First thing I want to do is write a function that gives me the population in terms of the time. All right. So what's the first thing that we need when we're writing a exponential growth formula?
All variables.
Okay, what's the first one that we need as we go left to right?
The principal, the initial amount.
Yeah. So what's the initial amount?
50,000.
Yep. So this population is 50,000. What comes after the 50,000?
1 plus R.
Right, 1 plus r. And in this case, what's r?
R is the 0.025.
Okay, so 1.025. That's 1 plus r. R is 0.025. And then I need one more thing to make that exponential. Oh, Aiden? What do I need to make that exponential?
You put a 1 at the top or x at the top because it's per u.
So the way I wrote the formula, we have to use a certain letter because of the notation. Yeah, so we used population as a function of t. So just make sure you put t. Okay, so there's your population. And now it says to use a graph to find when the population is 100,000. So if we want to do that on a graph, how about, Jacob, what would I put in y1?
Y1.
Yeah.
If it's, it would just be the equation, would it not? 50,000.
Yeah. So 50,000 times 1.025. On the calculator, you can't use the t, you got to use the x. And what would you put in y2? Yeah. 100,000. Now, as far as a window, I can see 1, 2, 3, 4, 5, 6. Yeah.
There should be 5 zeros.
100,000. 1, 2, 3, 4, 5. Yeah, 5 zeros.
Sorry, I thought you were counting zeros.
So what's the smallest amount of time that could go by? Yeah, 0. You could just say we're going to just look at the population to start and not have any time go by. The most number of years that could go by, well, there's really no limit. We don't know. Let's assume that it hits 100,000 people within 20 years. If it doesn't, we'll have to go a little higher. What's the minimum population that we could have? Yeah, we're not going to go below 50. And we want to know when it hits 100,000. So let's just go a little bit above. Okay, so there's our population. I don't think I went far enough. We want to know when it hits 100,000. So it doesn't happen within 20 years. So let's go out to, let's try 35 years. As long as it hits the top of the screen or gets pretty close to it, then I know I'm going to be okay. Yeah, that's fine. Okay, so there's the population growing. And to find where it hits 100,000, we have to calculate the intercept. Okay, so second calc, intercept. It's going to take 28.07 years.
So a little over 28 years.
A little over 28 years. Another way I could have asked that question to you is when, given all the information, when would the population be doubled? 100,000. Okay, same question. Okay, so as always, when you graph, be careful about including negatives. A lot of times negatives don't make sense because we're usually measuring time. Can't have negative time. And an amount. Can't have a negative amount. Now, I want to look at a problem where we have something doubling. Okay, so this is growth, but it's specifically doubling. What? Let's go back to the formula. What is your growth rate if something is doubling? Like I already told you, if something is halving, it's 50%. That's a 50% growth rate. What's your growth rate if something is doubling? Yeah? No, 200% would be if it was tripling. Yeah?
100%.
Right.
Because you're adding on to it 100% already.
Because you're adding on to 100% already, right. So if I said to you, I'm going to give you a 100% increase. If you had a 70 and you get a 100% increase from that, that's 140. Okay, I increased your grade by 100% of what it was before. So it was a 70, I added another 70. I added 100% to your grade. Yeah?
It's kind of like if R is 100%, turn to a 1.
Right.
Then it's 1 plus 1 is 2.
Right. So if this was for something doubling, this number would be a
2.
A 2. Yep, exactly. So
How is it not 2? Well, how does that work for? How does that work for percent-wise? Because you said 100% is like tripling.
100% is double. So if you had 100%, it would turn into a 1. And our formula is 1 plus r. And if r is a 1, 1 plus 1 gives us a 2. Okay, so that's the formula for something double. It still uses an initial amount. But the exponent, we just have to be careful, is t divided by the length of time to double. Because let's say something took 10 months to double. After 10 months, how many times would it have doubled?
Depends on the rate.
If it doubles every 10 months.
It doubles once.
It would have doubled once. It wouldn't have doubled 10 times in 10 months. Not if it takes 10 months to double.
Since t is equal to the amount of since t is equal to the amount of years that have passed.
Yeah, so like if 50 years had passed, or 50 months had passed, and it takes 10 months for something to double, how many times would something double in 50 months if it doubles every 10? 5. So you'd have to take 50 and divide by the length of time to double and realize that that's the number of doubling cycles. So the exponent is really the number of doubling cycles. That's what the exponent is. Okay. So what would be the formula for this one? Let's do the amount of bacteria as a function of time. What's your initial amount? Yeah. Yeah. Starting with 100. And when you're dealing specifically with doubling, you don't need to do 1 plus r. It's always going to be what when it's doubling? Inside the parentheses. Yep.
2.
It's always going to be a 2. Because doubling means 100% growth. So that's 1 plus 1 in the parentheses. And what else do I need to make that exponential? Yep. T. Yep. And to figure out when you hit 350,000 bacteria, you do it just like we did the population. You put 350,000 in one of the y's, put the formula in the other one, and then see where they cross. Okay, any question on that before we look at the last formula, which is the opposite of doubling, it's halving. Okay, so what did I say the rate is if something is getting half as big each time? What's the rate if something is getting half as big? Yep.
0.5.
It's 0.5. So if something is decreasing, it's decaying at a 50% rate, you just said it was 0.5. What's 1 minus 0.5? 0.5. That's the exponential half-life formula. It's the initial amount. And then this is a 1/2. Everything else is the same as doubling. Just the base is a 1/2 instead of a 2. And the idea of half-life is it's the amount of time for half of something to break down nuclear material. A lot of times half-lives are very long. They're in thousands of years. So let's say you start with 1 million pounds of radioactive waste now. In 1,000 years, you'll have half of that. In another 1,000 years, you'll have half of that. But that's a really long time, right? It takes a while. And it works exactly the same as doubling. Usually they'll tell you something like you got an amount. Yeah, they'll give you an amount. I'm not going to go through this one, but they'll say you got 5 grams to start with. The half-life is 20 days. And you just write a formula. 20 times 0.5. Or no, I'm sorry, 5 times 0.5 to the t over 20. Just like the last one. Yeah. No, you're right. It never reaches 0. Eventually, it gets so small that it's insignificant, or it reaches a threshold where it's no longer, like if it's radioactive, it's not as harmful. But it never goes away completely. It's always there a little bit. Yeah. Okay, so that's exponential functions. So let me, I'll put the homework up, and then while you guys are at lunch, I'll just go through and put a list of topics at the end of the video. Yes. Homework? Yeah, let's take a look.
So, well, it's 18 problems.